Hello.
Done. You can do it now.
Okay. No. So is it visible to all of you? So Anirbandha,
Yes.
is it visible?
Yes. Yes. It is visible.
Okay. So now,
So
so
make it
the topic,
full screen. Make it
yes,
full
it is.
screen like what we did.
It is full screen. I think I have to just increase this font.
Then probably remove this left hand side. Means it's okay. Means just it is fine. Means keep it like this. Okay.
Okay. So I think now it is clear, right? So title of my talk is this teleportation. About teleportation, I would like to talk, but I would not go to the continuous variable teleportation. I will only restrict myself to only this discrete variable teleportation. So here also we have written that known but hidden facts. So teleportation is a very common topic in quantum information theory, and maybe you know. Much about the teleportation. So it is a known fact, but something which is known to you but you don't know the details of it, and that is why this is a hidden fact also. So I will talk about this conventional protocol of quantum teleportation. First of all, I will start from this one, and then I will talk about I will talk about this classical teleportation fidelity, and then efficient resource state for quantum teleportation, then singlet fraction and its usefulness in teleportation, and then upper bound of singlet fraction. Then I will discuss the recent accepted paper, and that is the teleportation based on maximum eigenvalue criteria. And then at last, I will talk about controlled quantum teleportation. So with this outline, let me talk about this conventional protocol of quantum teleportation. So the conventional protocol of quantum teleportation is given by Bennett and et al. And this is the first protocol where this quantum teleportation has been introduced. Okay, so the objective of this protocol is to transmit the structure of the object between two distant partners, Alice and Bob, by sending only two classical bits. And here we assume that we can do this just by sharing only one EBIT, that is one entangled state we have to share. Otherwise, we cannot transmit the structure of the object between two distant partner with better than the classical methods. So here one thing we should note that we are teleporting, or we are sending the structure of the structure of the matter, but not actually the matter. We are not sending it. So it already present at the final location, and it vanishes from the initial position. That means it is lost from its initial position, and it then reappear in the at the receiver side. So this is the objective of this protocol of quantum teleportation. And then now, I will give you a brief description of Bennett et al. Protocol that we have, that we call it as conventional quantum teleportation. So let me first explain this thing in a pictorial way. So this is the conventional quantum teleportation protocol. Now we can describe this in this way. So let us suppose this is Alice, and she is the sender of the. She want to send some information to some other partner, Bob. So she is working in this laboratory, and it is described by this Hilbert space HA. and then its distant partner is Bob, which is who is the receiver of the who received the information sent by Alice, and he is working in another lab which is very far from the Alice's lab, and it is described by some Hilbert space HB. So now Alice encodes his information in this state, that qubit 1, and this it is mathematically, this qubit is given by this form, that is alpha 0 plus beta 1, where these alpha beta are complex numbers, and the restriction should be there, that is mod alpha square plus mod beta square should be equal to 1. So with these restrictions, the qubit is defined, and then Alice just encode his information in this qubit and want to send this information to his distant partner Bob. So how how she can manage this, how she can manage to send this information from one place to another place. So what she will do, first of all, this Alice and Bob shared a entangled state, and that is given by this 2 qubit 2 and 3, this qubit 2 and qubit 3. And let us suppose that this entangled state is given by one of the Bell state, that is maximally entangled pure state. So one of the there are 4 Bell state, and we have taken only taken among one of them. And let us suppose this the qubit 2 and qubit 3 is entangled, and this entanglement is described by this state B23. So now after this we have Alice have this qubit 1 and 2, and Bob has only qubit 3. So what Alice will do, Alice just take the tensor product of these two states, that is psi 1 and the B23. So that means with this 3 qubits, this tensor product structure will now give you a higher dimensional state, and this is described by 8 basis state, and this tensor product is given by the last step, that is 1 by root 2 alpha 0012. This means alpha 01 plus beta 11 tensor 0023 plus 1123. This tensor product can be expressed in this way, that is alpha 001 tensor 03 plus alpha 01 tensor 1, beta 10 tensor 0, and plus beta 11 tensor 1. So here we have written in this way so that we can understand that the qubit 1 and 2 is with Alice, and the third qubit is with Bob. So now in the in the conventional way, what we can do, or you can see the PRL paper of Bennett and et al. So there what they can do, they have done just convert this computational basis, that is 00011011 into the Bell basis, and then make a Bell state measurement on the qubit, so that the Bob received the qubit which Alice wanted to send. So but here we know that from the practical point of view, it is very difficult to realize all the 4 Bell states. So it is very difficult to realize all the 4 Bell state in the measurement in experiment. So so what we will do, we just take an alternative approach to explain this thing, and then in this alternative approach, what we have done, we have just used this C0 operations, that is the unitary operation, 2 qubit unitary operation, and this is known as C0. Also it is known as C0 gate. That means that here we have the first qubit 0 and the second qubit 0. The C0 gate tells us that if the first qubit is 0, then the second qubit will remain as it is, and if the first qubit is 1, then the second qubit will flip to the to another one. So that means if 0 is the first qubit, then 00 gives you 00, and if 0 is the first qubit in the second state, that is 01 goes to 01, 10. So here first qubit is 1, so that means the second qubit 0 flip to 1. So that means 10 goes to 11, and 11 goes to 10. So this is a unitary transformation. And if Alice apply this unitary transformation on his qubit, on his 2 qubit, that is 1 and 2, she poses with her. So then after doing this, this state will reduce to this one. So here you can see that alpha 0 0, so first one is 0 0, so it will remain the same here. 0 1 also remain the same here, and here you can see beta 1 0. So 1 0, when we apply, when Alice apply the C0 operation, then 1 0 will become 1 1, and then 1 1 will become 1 0. Okay, so in this way we can rewrite this in this form also. Alpha 0 1 tensor 0 0, this upper part can be written in this form also. So 0 1 tensor 0 0, alpha 0 1 1 1, like this. After writing this, Alice just apply the Hadamard gate transformation. So here the Hadamard gate transformation is given by this one. 0 goes to 0 plus 1 by root 2, and 1 goes to 0 minus 1 by root 2. So, so then first Alice apply the unitary C0 operation on his 2 qubit, 1 2. After applying the C0 operation, she then apply the unitary operation, Hadamard gate operation on his first qubit. So after applying this Hadamard operation on his first qubit, the resultant qubit, resultant state will now this one, that is it is given by this chi double dash. And it is given in this form: 0 0 1 2 tensor alpha 0 plus beta 1 3. So that means this above state, after the operation, after the Hadamard gate operation, this state reduces to this upper one, this state reduces to this one. So 0 0 1 2 alpha 0 plus beta 1, and 0 1 alpha 1 plus beta 0. In this way we can write this output state. So now this is a totally mathematical way of doing this. So now after this, what Alice will do now? So here you can see that this state will go to this alpha 0 plus beta 1 will go to the receiver side if only Alice performs some measurement on it. So here you can see because we have some difficulty in performing Bell state measurement, so Alice can perform here the computational basis measurement. So here Alice can perform computational basis measurement with the computational basis 0 0 0 1 1 0 and 1 1. So when Alice perform this measurement, so let us suppose if Alice performs some measurement on it, and just when she perform measurement, the entanglement will lost, and the input state that Alice has, that will vanish. Okay, and then this input state then reappear at Bob's side, either in this 4 form. So either in this form, or in this form, or in this form, or in this form. Okay, so that means Bob can receive either this one, or this one, or this one, or this one, but actually he don't know which state he received from Alice until Alice gives some hint to Bob. So this thing just relativity no signaling it discard the no signaling operation, that is signaling is not happening here, because unless Alice gives some information to Bob, Bob don't know which state will he receive. So that means Bob can receive either in this form alpha 0 plus beta 1, or alpha 1 plus beta 0, or alpha 0 minus beta 1, or alpha 1 minus beta 0. These 3 states are represented by these 3 figures. These 4 states represented by these 4 figures. So now what Alice will do, Alice then call to Bob that which measurement outcome she obtained after measuring the after performing measurement in the computational basis. Let us suppose if Alice inform Bob that I have just getting this outcome 0 0, then Alice has to do nothing. Then Bob has to do nothing on his qubit, because alpha 0 plus beta 1 is the input state, and if Alice measures measurement result is 0 0, then he has to do nothing. But if Alice told him or tell him that the outcome is 0 1, then the state will be at the Bob's position is in this form alpha 1 plus beta 0. In this case, Bob has to make some unitary operation on it, or perform some single qubit measurement on it, so that it will reduce to not a single qubit measurement, it is a single qubit unitary operation he can actually apply on it, and then he just reduces the state to this one. So if alpha 1 plus beta 0, so if Bob applies sigma x here, then this state alpha 1 plus beta 0 will reduce to alpha 0 plus beta 1. In the same way, if alpha 0 minus beta 1 and alpha 1 minus beta 0, so alpha 0 minus beta 1, if Bob receives, then he has to apply sigma z operation, and then if he receive alpha 1 minus beta 0, he has to apply sigma y operation. So in this way, after getting some signal from the Alice, after getting some information from Alice, Bob has to recover or reproduce the initial state at his site. So after receiving the information from Alice, Bob can receive the actual input state that Alice wanted to send. And you can see that alpha 0 plus beta 1 is the input state, and the final output state is also alpha 0 plus beta 1. So that means if you take the overlapping between this input state and output state, that overlapping gives you 1. So that means the fidelity is 1. But what cost we have to bear from it? That cost is the classical communication. So that means Alice has to make classical communication with Bob, and with this she has to inform Bob about this measurement result, and she has to spend 2 classical bits to send classical information from her to Bob. So this is the conventional protocol of quantum teleportation protocol, and it is given by Bennett et al. So after describing this one, so let me talk about some classical teleportation fidelity. So here you can see that in the quantum teleportation part, we can send the input state with unit fidelity to Bob. But we have to talk about the classical part also, because in Bennett et al. Protocol we have used the entangled state, and it has no classical analog. So that means we have just used the quantum part there. But if we don't have this type of thing, means quantum mechanical thing in our hand, then what we can do our best with the classical tools that we have in our position. So to do this, we can assume that the state to be teleported is a qubit. So that means the state which we want to teleport is a qubit. That means it can be written in the form alpha 0 plus beta 1. So this is a quantum state. So this is the only quantum which we want to send from one place to another place. We are not sending any classical state, but a quantum state from one place to another place. But we will use some classical tools here. So what we will do here, so we have to take only the single copy of a qubit. So we don't have any multiple copy of a qubit, but here we are considering a single copy of a qubit. So now the question is, that if we have a single copy of a qubit, and if we want to transmit that qubit from one place to another place without using entanglement, but using only classical tools or classical methods, then how much information we can send from one place to another place? That would be the question. So how much fidelity? That means let us suppose the state to be teleported is psi. That is, psi is in the input state. Psi is the input state, and after teleporting to this qubit to another place, so that the Bob receives some qubit, and that qubit may be expressed as phi. So now we to calculate the fidelity, we have to take the overlapping between these two, psi and phi. And now our task is to do what would be the maximum value of this fidelity when we are not using a quantum entangled particle or quantum entanglement as a resource state. So to do this, we can adopt this prepare and measure strategy. So this strategy tells us that just take a single copy of a qubit and measure that qubit. And when you measure the qubit, since it is a quantum state, so it is lost after measurement. So that means you have to prepare again that qubit. And here we assume that we can prepare the same copy as we did in the first case, as we did in the first earlier. So the copy will be same. We assume that because in the quantum context there is a no cloning theorem, so we cannot exactly copy a single quantum state. Single quantum state cannot be copied, but we have assumed that if we have some procedure by which we can construct the same copy, that means in principle we can construct the same copy. So if we are able to do this, then we can just prepare that copy and then again measure on it. Okay, so in this way we can just prepare the qubit and then we can perform measurement on that qubit and extract information from there. And in this way, if we do this infinitely, and then we can extract some information. So in the real lifetime we cannot do it infinitely, but we have to restrict ourselves in a finite time. So that means when we have extract information from that one, and then we will send that information to Bob to recreate that state. Okay, so when Bob recreate that state based on the information given by Alice, then he creates some state that is phi. Okay, but Alice wanted to transmit this state psi. Okay, so in this prepare and measure strategy, Bob can recreate the state, but not actually what Alice wanted to teleport or wanted to send the state. That is not perfectly done. So that means the fidelity psi phi is never equal to 1. So that means here the question is, so what would be the optimal measurement strategy we can take so that we can send the information as much as possible to Bob? Okay, so that procedure is given by S. Messer and S. Popescu. So this is given in 1995. And they have given the optimal procedure just by using this prepare and measure strategy, and then how much optimal information Bob can get from Alice. That means optimally how much state, the state which Bob create, that is when it matches with the initial state of Alice, then what would be its maximum fidelity. So they found that when we are using this optimal measurement strategy, then this fidelity will be 2/3 and not beyond this. So that means we can have this thing in general. We can say that the classical fidelity means when we are not using the entangled state, or when we are not using any entanglement or any quantum mechanical phenomena in this context. So we have done only with the classical thing. So the measurement strategy is also classical, the measurement apparatus is also classical. So only with this classical tools we can just measure the fidelity, and that fidelity never go beyond 2/3. So the optimal fidelity, classical fidelity, is 2/3. So that is why we are saying that when we are performing this teleportation protocol, so if the teleportation protocol is gives you the fidelity greater than 2/3, then only we can say that it is quantum teleportation. Otherwise it is not quantum teleportation, it is classical teleportation only, if the fidelity is less than equal to 2/3. So you can see if you go through the if you want to go. Yes.
Satyabrata, this is probably not a tight statement, because I can have a quantum fidelity, but in noisy channel it can give a, well, quantum teleportation, but in noise, means presence of noise, it is getting less than 2/3. So then it is not useful, but it is still, I cannot say it's a classical. So if it is
No,
greater
no,
than
that is a
2/3,
different thing.
then only it
No,
is
no, no.
useful as a quantum teleportation. Otherwise, it's there is no sense of using quantum resources for doing that. But
No, actually,
quantum, you
so
implement everything with quantum resources, but still you can get less than 2/3 for
you
noise.
were you were talking about the single qubit or entangled qubit?
No, what I am saying that this 2/3 boundary is, that means when you do a quantum teleportation, then you can claim, if it is greater than 2/3, then only you can claim that it is useful because it is giving better than classical.
Yes.
Suppose you start with that, and because of application of noise, it reduced to below 2/3. So still it will remain quantum, but it will not be useful because it is giving the less than classical fidelity. So
No, that is a
2/3 is
different
not a
thing.
boundary
No,
between
no, no.
class.
Anirbandha, that is you are talking about totally different facts. So I will go to this point also in my later slide. So
Okay.
means in the teleport, if you have some mixed entangled state, then it may give you the fidelity less than 2/3, but it may be useful just by applying the local filtering operation. So I will come to that one later one.
No. Even if you are starting with something, when some absolutely entangled state, you are just applying Bennett's protocol. And in Bennett's protocol also, if the noise is higher, then in a noisy situation, it can go below 2/3. But then still it will remain quantum, but it will be useless because it's less than 2/3, and I can achieve 2/3 by classical means also. But
Yes,
so
I am also
2/3
saying
is
that
a boundary.
no. I am also saying the same thing, that if the classical fidelity is less than 2/3, it is not, we cannot say that it is a quantum teleportation. But if it is greater than 2/3, then only we can say that we can teleport it
No,
quantumly.
it's not about whether it is quantum or classical. It's quantum is useful quantum or not, because even if it is less than 2/3, if you are using resources, quantum resources, it will remain quantum, but it is a useless, means it is not going to give, it has no quantum advantage.
Quantum teleportation means when we are saying that classical fidelity is greater than 2/3, because it is useful in that sense.
Okay.
Useful and
Huh.
quantum, it is only useful because we can use that quantum nature of that. So it is useful and quantumness, they are interrelated. They are connected with these two things. Okay, so that means you can even say that it is less than 2/3, but it is still quantum, but it is not useful.
Yes,
Okay.
that's exactly.
Yes, but I am saying the different thing. I am saying that quantum teleportation and classical teleportation, what is the difference between these two? Okay, so classical teleportation is also there and quantum teleportation is also there. So when we can say that it is classical teleportation, when we can say that it is quantum teleportation. So when fidelity is less than 2/3, you cannot say that it is quantum teleportation. It is classical teleportation only, but the qubit is the quantum in nature. So I am not denying that fact that it is not in quantum, but I am just giving you the distinction between the classical teleportation and the quantum teleportation. Fine. So this is the thing. So if the classical fidelity is less than, or the maximum value of the classical fidelity is 2/3, and if it is go beyond 2/3, then we can say that we can achieve the quantum teleportation. So now
I have a question here. May I ask a question here? So
yes,
what are we actually comparing? Because
we are comparing the classical teleportation. What do you mean by classical teleportation?
I'm asking about the fidelity, because fidelity will depend upon the values of parameter of the state we are teleporting, alpha and beta. So are we actually averaging over alpha and beta when we are comparing with the classical bound, or
yes, we are taking the average.
so shouldn't we call that average fidelity then? Because
yes, average fidelity you can always talk, because we can always have to take into account the average fidelity, not only fidelity, but in general we are talking about fidelity, but it is average fidelity only.
But isn't it itself like complex in that sense? Because we are starting with the argument of single shot teleportation, right? So we prepare a state, we are teleporting it, and we are talking in that sense, and then we are averaging over all the parameters of the state.
Yes.
So in general case, There may be a state which may be teleported with unit fidelity, and there may be another state which may not be teleported with fidelity 2/3. But when we are averaging over input parameters, then average is more than 2/3.
Yes.
So,
but here you were talking about when you were considering the entanglement. But here I am not using any entanglement, but prepare and measure strategy we are adopting here. So when you were talking about the quantum entanglement, and with that entanglement as a resource, you are sending some qubit state to Alice to Bob, then you are averaging all these things. So here averaging is the different thing. Okay, so I would like to show you this this paper. You can just see this paper, and it talks about the actually it will give you another 2-hour talk to explain this paper, because this is a very good paper, and if you want to have this classical fidelity, how a classical fidelity is obtained as 2/3, because many of you don't know how we can have this classical fidelity 2/3. And if you read this paper, then you have the clear idea that how we can get the fidelity 2/3 just by adopting prepare and measure strategy, and just by using this classical tools only. So we are not using any entangled state. We are not
but
using
that will
any...
require multiple copies, right? We cannot do classical
Yes,
teleportation with single sort.
Kishore, I think
because it is you can see here, this is given for n copies, but if you put n equals to 1, then you will get it 2/3.
Yeah. So hi,
Okay.
Kishore, I think one can talk about the ensemble average in this context. Surely you can. I think averaging over the state parameters won't make sense, as you put rightly.
Exactly.
Yeah,
because
we
have to average over this, because there you can see that in the last line you can see that they found an optimal measurement cannot be realized by separate measurement on each particle. So that means the optimal measurement strategy by which equality can be achieved. And you can see here, if you see this abstract of this paper, then it is clearly written that the optimal measurement procedure must necessarily view the ensemble as a single composite system rather than as the sum of its component. That is, optimal measurement cannot be realized by separate measurement on each particle. So so I'm not discussing in detail this paper, because it will take time to discuss about this paper. So I'm just highlighting these points what they have mentioned in their paper. And just using their result, we can see that the classical fidelity is always less than equal to 2/3, and it doesn't go beyond 2/3. So may I go further? May I proceed?
Yeah, sure.
Okay. So now this is a quantum channel that could be useful for communication purposes only if its teleportation fidelity exceeds 2/3. Okay. So pure maximally entangled state, as we have seen, that it is the most efficient resource state for quantum teleportation. But in this 1996 work of Orodeki, they have shown that not all entangled mixed states are useful for teleportation, because there exists some entangled mixed state which at that time it is not known that mixed state is useful for teleportation, but later we know that all entangled mixed states are useful for teleportation. But in 1996 we don't know. So if we talk about this context, then we can say that not all entangled mixed states are useful for teleportation. But now the question arises that whether like maximally entangled state, maximally pure entangled state, so can we have this maximally entangled mixed states also, and if we can use that maximally entangled state as an efficient quantum teleportation channel. So to understand this maximally entangled mixed state, let us take this definition. What do we mean by maximally entangled mixed state? So the states that achieve the greatest possible entanglement for a given mixedness are known as maximally entangled mixed states. So if some state is given to you, and if mixedness is given, then the highest possible entanglement gives you the among those among those mixed state with the given mixedness and the highest possible entangled mixed state is known as maximally entangled mixed states. And this notion of MEMS was first introduced by Ishizaka and Hiroshima. And there you can see that maximally entangled mixed state. And now there is a very important property of this is that if you apply some global unitary transformation, if you apply some global, not a local, global unitary transformation, then its entanglement not after that means if you apply some global unitary transformation on it, then it increases the entanglement. And then after some critical value of the entanglement, if you further apply this this global unitary transformation, it will not increase any entanglement. So if this happens, then we say that mixed state is has achieved the maximum entanglement, and that mixed state is known as maximally entangled mixed state. So they proposed a class of bipartite mixed states and showed that entanglement of those states cannot be increased further by any global unitary operations. So later Munro and et al. Studied a class of state which has the maximum amount of entanglement for a given degree of purity and derived an analytical form of that class of MEMS. There also exists some NMEMS, that is non-maximally entangled mixed states. So there are also this, let me give you this structure of this one. So this is the non-maximally entangled mixed state. So if we consider this non-maximally entangled mixed state, that means you can construct this. Let us take a GHZ state and just one qubit you can partially traced out. Then you can have rho 1 2 G, and then if you take a Werner state, W state, and if you trace out one qubit, then you will get rho 1 to W. And if you take this rho 1 to convex combination of rho 1 to G and rho 1 to W, then you can define this as the new mixed state. And we have proved in this paper that this is a non-maximally entangled mixed state. That means there exists some entangled mixed state whose entanglement is greater than this one. So in this way we can define the maximally entangled mixed state and non-maximally entangled mixed state. And then we can now we can pose this question whether all maximally entangled mixed state could be used as efficient quantum teleportation channel. But this is not the answer of this question is no, because we found that there exists a Werner state which always acts as better teleportation channel for all finite value of mixedness, even though they are less entangled compared to MJWK states, that is Munro states, for a given entropy. So I have already this is now 7:45, so I will go a little bit faster.
Oh, no, you can continue with this speed. Means we are not in hurry.
Okay, so that means I should not be in a hurry, right?
No, you can. I mean,
Okay.
speak in a speed where the student can follow.
So then let me. Okay, so then let me show you this MJWK state. So this is the form of Munro et al. That is MJWK state. This is the form. That is equation number 25. This is maximally entangled mixed state, where HC, this is the function of C. C is the concurrence of this state, and this HC, that is function of C, is defined as C by 2 when C is greater than 2/3, greater or equal to 2/3, and it is 1 by 3 when C is less than 2/3, and C denoting the concurrence of rho MEMS. This is the form of the MJWK state. And if you want to see the Werner state, so the Werner state is given by this form: 1 minus FW, where FW is the maximum singlet fraction. So I will talk about singlet fraction a little bit later. So this is the form of the Werner state. And if you compare these two states, then you can find then you can find that this Werner state always act as better teleportation channel for all finite value of mixedness, even though they are less entangled compared to MJWK states for a given entropy. So that means, Yes.
Is MEMS state and MJWK state, they are same, or they are different? How they are different? MJWK and MEMS state.
Yes, MJWK state and any MEMS state, there may be some state which is different from MJWK state. For example, this is Warner state. Warner state, if you take the class of Warner state for some for this given mixedness, so it has some value, it has some maximum value of entanglement, and in that set it is maximal entangled mixed state. So when you are defining the maximal entangled mixed state, that means you are confined yourself in as you have to take some class of states, not for any state in general, because we are defining the maximally mixed state. That is, here you can see the definition that for a given mixedness, here it is given that for a given mixedness, and the mixedness of any state is not same. If you consider all the mixed entangled state, or in fact if you consider any mixed state, so the mixedness is not same for any mixed state, right? So we have to consider for the given mixedness. So, for particular value of mixedness, we have to take all set of states, and we have to find out the which mixed state gives you the maximum entanglement.
Is
And
Monroe
that,
state?
that's it. Yeah. Yes.
Yeah, is Monroe state is a subset of MEMS, or?
Yes, subset of MEMS. So here you can see that the Warner state act as a better teleportation channel, but its entanglement is less than MJWK state. So that means MJWK state its entanglement is better than the Warner state. But when we are talking about in terms of teleportation, then Warner state always acts as better than MJWK state. So that means we cannot say that all MEMS state could be used as efficient quantum teleportation channel. So in our work, we have also constructed this non-maximal entangled mixed state and found that the newly constructed non-maximal entangled mixed state can serve better as quantum channel for teleportation compared to Warner derivative, which is also a non-maximal entangled mixed state for a range of values of mixedness. So this is all about the maximal entangled mixed net, but the important point is to find out the relationship between the singlet fraction and the teleportation fidelity, and it is very, very important because when we have started, we have seen that we have used this maximally entangled state, maximally pure entangled state as a resource state. So now, always it is not happening that we get this maximally entangled pure state, because when we have generated some 2-qubit state in a lab, then to use this as a resource state, or to use it in a teleportation channel as a teleportation channel, we have to send one part of this pair to its to some other party. And when we will do this, then we have to send this with through the environment. And when we are sending this qubit through the environment, then it must interact with the environment. It must interact with some foreign particles with the environment, which is in the environment, and then this disturb the state, and the purity will be lost, and the reduced state will be now mixed state. Okay, so that means in general, or in reality, in experiment, what we will get, we will not get the pure state always. We will get in many cases that the mixed state. So we have to deal with in generality we have to deal with the mixed state. So now the question is the state which we are considering as a resource state, if that state is a mixed state, then how much it is closed with the maximally entangled state, maximally entangled pure state, because this defines this quantity F rho AB. Okay, this defines this quantity F rho AB. So that means we have to take the overlapping between the state rho AB, that is a mixed state, and the maximally entangled pure state. So how much it is, how much it closes with the maximally entangled pure state. Because if we have this rho AB equals to rho AB is a pure states, that is if it is one of the maximally entangled Bell state, then we can see that the value f rho ab, the value will be equal to 1. Okay, so the value of the f rho ab equal to 1, and in this case there is a relation between the teleportation fidelity and the singlet fraction, and it is given by Adhikari. And you can see that if f rho ab equals to 1, then the teleportation fidelity is always equal to 1. Okay, so that means this is a correct measure that and that should be related with the teleportation fidelity, because this quantity measures the amount of the teleportation fidelity, amount of teleportation fidelity when the resource state is not a pure state but it is a mixed state. Okay, so this is a very useful relationship between the teleportation fidelity and the singlet fraction. So here you can see that if f rho ab is less than equal to 1, less than equal to 1 by 2, so that means it's less than equal to 1 by 2, that means you can see that the teleportation fidelity will be less than equal to 2/3. So when the teleportation fidelity is less than equal to 2/3, then we can see that it is means we cannot use it as a resource in quantum teleportation. Then the state rho ab, which is the shared state, that shared state is useless. It is not useful in quantum teleportation. But if this value of the singlet fraction is greater than half, if we find that the value of the singlet fraction is greater than half, then we can see that the teleportation fidelity is always greater than 2/3, and we can say that this resource state, or the state which is shared between Alice and Bob, is useful in quantum teleportation. But here we can find that there exists some entangled states whose singlet fraction is less than half. So that means there exists some entangled state which is not useful, which is entangled, but which is not useful in quantum teleportation procedure. So now the question is, if there are mixed entangled state with singlet fraction is less than half, then can we conclude that these entangled states are not useful for teleportation? This is a vital question. No, the answer is no, because this Barzak, Adhikari, they have given a procedure by which we can increase the singlet fraction. But you don't have to worry about that this procedure is global one, but the procedure is local one, because they have used some local operation. They have used some local operation on the given entangled state, which is whose fidelity, whose singlet fraction is less than half, and just by using this local operation, they can increase the value of the singlet fraction. And we have some example of this type of states whose initially whose singlet fraction is less than half, but after applying the local operation, this is known as local filtering operation. So after applying this local filtering operation, the singlet fraction will be enhanced, and it will become greater than half. So they have shown that interaction with the environment can enhance interaction with the environment. This means that they have used some local filtering operation. That means they have not used any unitary operation, but they have used some local filtering operation. And using this local filtering operation, they can they have shown that the singlet fraction can be enhanced, and it may go beyond half. And the state which is initially not useful for teleportation, and now after applying the filtering operation, can be useful in quantum teleportation. So then it is this paper is talked about, this Badziak paper is talked about few type of state, or few class, some class of entangled states, but they have not given any filtering operation which works for all type of mixed state. So now the question is, can we do this same procedure, and can this same procedure work for all mixed state? So that means, can we apply this local filtering operation to any mixed 2-qubit mixed state, so that if it is not, if its singlet fraction is not less than half, then can we make it can we enhance the singlet fraction and make that singlet fraction greater than half? So this question is addressed by Versatrate et al., and they have derived an important relationship between the singlet fraction, local filtering operation, and partial transposition of a given mixed state. And they have just used this singlet fraction. They have obtained this expression of the singlet fraction after applying local filtering operation, and they have obtained this one half minus trace of x rho gamma, where gamma is the partial transposition operation. So you can see that if rho AB is entangled state, then since it is a 2 cross 2 state, means we are talking about 2 qubit state. So it is so partial transposition operation by which we can detect whether the state is entangled or not. So it is a necessary and sufficient condition. So that means rho AB gamma. So if rho AB is entangled state, and then if we apply this partial transposition operation, then we can we know that the after applying this partial transposition operation, it will not remain a physical state, and it will be a non-physical state. So that means when we have rho AB, so this is a semi-definite matrix and it has all eigenvalues positive. But after applying this partial transposition operation on it, so it will not be a physical state. That means it will not remain in a positive it will not keep its positive semi-definite form, and hence one of its eigenvalues is negative. And hence, since one of its eigenvalues is negative, so from this you can roughly say that this minus will become plus, and hence half plus this quantity. So this means that we can say that for any rho AB, for any 2 qubit density matrix, the singlet fraction will become greater than half, and we can say that the singlet fraction is greater than half for all mixed state rho AB. So this results is published in 2000, I think 2003, and here it is written that they have shown that any entangled 2 qubit mixed state can be used as a resource for quantum teleportation using certain trace preserving local operation and classical communication. So that means since they have shown that the singlet fraction can be made greater than half for any mixed state, any 2 qubit mixed state. So from this we can conclude that any entangled 2 qubit mixed state can be used in quantum teleportation as a resource state. So now, after this singlet fraction, after they have given this singlet fraction, now the question is whether it gives you the optimal value. So they claim that it is optimal, but we mathematicians not always believed in what they are saying. So we have done a work on it, and then we have addressed this question, that is this singlet fraction obtained by Versatrate et al., it is the maximal possible value of the singlet fraction obtained by local filtering operation. Is it the maximal? They are saying about maximal but not maximum. So we are investigating that whether it is a maximum or not, and then we found that no, it is not a maximum value. No, this value is not maximum, but we can get some value which is bigger than this FB rho AB. So we have demonstrated a new method to achieve the maximum singlet fraction using local filtering operation, and this method is given in this paper, which is published in 2016. So we have established a tight upper bound on singlet fraction and showed that the maximal singlet fraction obtained by Versatrate and Versalde does not attain the upper bound on the singlet fraction. So in this paper we have given this bound, and this bound is given by this z plus eta 3/2. So there is some meaning. So rho AB4 means this is a 2 cross 2 matrix, 2 cross 2 system. So it is a 4 qubit 4 cross 4 matrix. Rho AB is given by 4 cross 4 matrix. That is why I have written here 4. So it is denoting the 2 qubit density matrix, and this 4 cross 4 matrix can be written in this form: rho AB3, where this is the single column vector, and this is the single row vector, and then this B is the 3/3 vector. This is B is the vector quantity, so that means it has three terms here, and here B star transpose, it also has 3 terms, and C is a constant value, and eta 3 is the maximum eigenvalue of rho AB3. So rho AB3 means this gives you the 3 cross 3 matrix. So this, if we decompose these two qubit density matrix, that is a 4 cross 4 matrix, means 4 cross 4 matrix can be decomposed in this way. And if we this eta 3 is the maximum eigenvalue of rho AB3. So in this way, if we have these values, then we can find that FD rho AB4, this bound is given by Dembo's bound. This bound is called Dembo's bound, and we can use this bound, and we can show that this value is greater than the value that has obtained by Versatret and Versilde in their paper. So after this, so actually we have investigated a lot about this expression. So first of all, we have investigated this about the upper bound, whether this upper bound gives you the maximal value or not. And then again we have some problem in it. The problem is that this they have applied this partial transposition operation here, but we know that this partial transposition operation is not a completely positive map, and since it is not a completely positive map, so it is not a physical operation, so we cannot apply it in an experiment. So now the question is, so if we want to estimate this value, then we have to measure it. And since gamma is there, that means partial transposition operation is there, and it is not a completely positive map, and hence we cannot obtain its value or estimate its value experimentally. So what we would like to do, we just make a structural physical approximation. So we have just use it a structural physical approximation. That means this approximation tells us that if some operation which is a positive operation but not completely positive, so just by applying this structural physical approximation, we can make it a completely positive operation. Okay. So, but it is an approximation, and hence we have to give some cost about after applying this. And then in this recent paper, just we have accepted this paper in International Journal of Theoretical Physics with my scholar Anuma Garg, and we have derived here we have addressed these questions if this Versatret singlet fraction where this partial transposition operation is applied, if this partial transposition operation is replaced by its structural physical approximation, then what will happen? So we then see that we then find that after applying this structural physical approximation, then this singlet fraction will not give you always this singlet fraction, this value is always not always greater or equal to half. So there exists, and we have also shown an example that there exists some state if we apply some structural physical approximation of the partial transposition operation, then the value of the singlet fraction may be less than half. And in that case, this expression will not valid. Okay, so so in this work, let me give you some hint about this work, that we have derived a criteria for a detection of d cross d dimensional negative partial transpose entangled state used as a resource in quantum teleportation. So we have derived some d cross d dimensional negative partial. So we have just we have not taken only 2 cross 2, but we have just go beyond that, and we have used this d cross d dimensional negative partial transpose entangled state that can be used as a resource in quantum teleportation. And that criteria that we have given is not based on the singlet fraction, but it is based on maximum eigenvalue of the NPT entangled state, the NPT entangled state which we used as a resource state, and the teleportation criteria depends on that maximum eigenvalue of that NPT entangled state. And we have used this maximum, we have take the help of the eigenvalue because it is easier to determine experimentally than to completely reconstruct this state via quantum tomography. So here you can see this paper by Eckert, Alves, and all other. So in this paper you can see they have shown that this that if you find the eigenvalue of some functional, and then you can always show that it can be determined experimentally easier than the tomographical methods, because in tomography you have to measure, you have to use a lot of measurement in tomographical approach. But if you find the eigenvalue, then it will give you lesser number of measurement, it will require lesser number of measurement. So here it is given that instead of singlet fraction, if the criteria is expressed in terms of the eigenvalue, then it requires lesser number of measurement than to completely reconstruct the state via tomography. So then in that paper, what we have done, that we have shown that this maximum eigenvalue of any d cross d dimensional density matrix rho, and that maximum eigenvalue is always greater or equal to singlet fraction, maximum singlet fraction. So just using this result, and this is just not very important result, but we have done this, that this maximum eigenvalue lying between 1 by d square and 1 but this lemma 1 is very useful, and we can use this lemma, and then we can show another theorem, that any arbitrary d cross d dimensional isotropic quantum state rho p shared between two distant partners is separable if and only if lambda max rho p is less than or equal to 1 by d. So that means here we proved it. We are able to prove this only for the isotropic quantum state, but not any quantum state. And we have proved that if the eigenvalue of isotropic, maximum eigenvalue of the isotropic is less than or equal to 1 by d, then we can say that this state is separable. And if this state is separable, then we can always have the lambda max rho p is less than or equal to 1 by d, where rho p is the isotropic state. So this result will be applicable only for the isotropic quantum state. So now we can have this corollary, that entangled quantum state rho shared between two distant partners is useful for quantum teleportation if lambda x rho greater than 1 by d. So if lambda x rho less than or equal to 1 by d, then we cannot say anything. But if lambda max rho greater than 1 by d, then we can say that it is. You can see here it is not an if and only if condition, but if this condition hold, if lambda max rho greater than 1 by d, then only we can say that the state rho, which is a shared state, it can be that state can be used as used in a teleportation protocol. And just using this one, we can have this teleportation fidelity, and the upper bound of the teleportation fidelity we have obtained in terms of maximum eigenvalue of the density matrix. So this is a very useful quantity that is given in the right hand side, because experimentally it can be obtained quite easily than the tomographical method. So I have just wanted to say this, but I have also wanted to tell control quantum teleportation, but I think I have done. I would like to stop here now. So if you have any questions, then you can ask. Yes.
Hello.
Yes.
Hello. What is the characteristics of a negative partial transpose?
Negative partial transpose means if you have entangled state, then if you make the if you perform some partial transposition operation, and if you get negative eigenvalue, then you can always say that this state is entangled. But in the higher dimensional system, that is beyond 2 cross 2 and 2 cross 3 system, you can have some entangled states whose you can have some entangled state. If you apply some partial transposition operation, then also it will be it will remain in a it will remain physical state. That means it will be a positive semi-definite operator, and it will give you only positive eigenvalues. So after applying partial transposition operation, if you get positive eigenvalue, then you cannot say anything about the entanglement. But there exists some state after applying some in a higher dimensional system, after applying some partial transposition operation, it will give you the negative eigenvalue, and that state will be called as a negative partial transpose entangled state.
Okay, thank you.
Anyone else has question? Mitali?
You mentioned in the last slide about isotropic quantums. So what is isotropic state? In the last one, yeah, just before this one. Yeah,
This one, isotropic quantum
group.
state.
Yeah.
So this is a type of state if you take the convex combination of the identity operator and the maximally entangled state. Sorry, 1 minute.
So how is it different from Werner state then?
No, 1 minute, just a minute. I will show you. Actually, I forgot the form of that one. Yes, this one. Sorry. Yes. P5 plus noisy singlet state and this isotropic state and yes, same thing, Werner state. But there is some slight difference between Werner state and this isotropic state. This is the noisy singlet state. Actually, it is called isotropic state.
Satyabrata, what is the isotropy here?
Actually, I think it will come from this one side, mixed state, I tensor I.
No, mixedness I can see, but the isotropy part it's not visible at least. It's isotropy with respect to what? Which parameter or state parameter?
With respect to mixedness, with respect to P actually, I think. With respect to the parameter P.
But even though if it is with respect to P, I don't see the isotropy here.
Yes, it is isotropic with respect to the parameter P.
Yeah, but how I don't see it in the from the this form of the state.
Yeah, this thing I don't remember this thing actually. Why it is isotropic? I don't remember.
Maybe it has a when you will write it in a different form, it becomes isotropic. It is also
what?
difficult.
Yes.
I thought maybe when you will rewrite it in some different form, it may become isotropic. But even then, it is very difficult to say, because if you already have some anisotropy and you apply a unitary operation to rewrite it in a different form, how the where the anisotropy will go. So it's not possible to convert anisotropic to isotropic.
Yes. I just It is given in the Horoghi paper. Yeah, I just remember this thing now. Recap.
Anyone has questions or whether specific query, or you need more clarification at any point?
Hello. What is the teleportation fidelity? Means what parameters it depends on?
Teleportation fidelity may depend on many parameters. Just you have to calculate the fidelity just using this formula, and if it depends on the parameter state, then it will depend on the parameter. That parameter. It will depend on the state parameter also. If you want to make it independent of the state parameter, then also you can make it independent of the state parameter.
Okay, but I means that what means the value of the teleportation fidelity? I means that suppose the
so when you calculate the teleportation fidelity just by using this formula, so you need to calculate this you need to calculate the singlet fraction. So if you want to use this one, otherwise you can use the input state and output state and overlapping between these two. You can calculate that one also. But if you want to this singlet fraction using this one, if you want to use this formula, teleportation fidelity, that is 2 into singlet fraction plus 1 by 3, then you have to just take the overlapping between this maximally entangled state in if you are taking 2 cross 2, then you have 4 Bell state. Then you have to just taking the overlapping between the singlet fraction of that state which you want to calculate, and then the parameter involved in this state will come into this singlet fraction. And when you substitute this value here, then the teleportation fidelity also depend on that parameter.
Okay.
And Satyabrata, when you talk about the MEMS state, so is it can we say for a given distribution, it's just the mixture of maximally entangled state? That's what it should be, right?
Maximum. Can you repeat?
I'm saying MEMS.
Maximally, you were talking about maximally entangled state.
Yeah.
Yes. Then.
So MEMS state can be realized as the mixture of the maximally entangled state for a given distribution, probability distribution. Is it?
No.
What else will change? Because any mixed state can be written as a some weighted combination of all states, and in order to have a maximal entanglement, there should be for a given distribution. They can be only the mixture of maximally entangled state.
So maximally entangled mixed state means what? Just if you follow the definition of the maximally entangled mixed state, then you can see that if you want to take the maximally entangled pure state, convex combination of maximally entangled pure state and some other state, right? So you want to take the convex combination of maximally entangled pure state and some other state.
What I understand from the acronym which has been used, or the name of the MEMS state, it should give the maximal entangled state of the mixture, of the mixed state. That's what. And now the question is, what can give the maximal entangled state, maximal entanglement of a mixed state? So since you are fixing the, so there are two possibilities. There are two things which we can change: either the probability distribution or the state itself. So because you are fixing the probability distribution, then the only thing remains is the state. And then if the states itself are maximally entangled, so the mixture of that should give the maximally entangled mixed state. That's the question.
Yes, if you further apply this global unity transformation, and if you find that after applying that global unity transformation, the entanglement will not change, entanglement will remain fixed at that point, then only you can say that the state is a maximally entangled mixed state. Otherwise, if you apply global unity transformation and entanglement will increase, then you cannot say that that state is a maximally entangled mixed state.
So taking convex combination of it will not create any change in the entanglement. It will still remain maximally entangled.
No. Actually, you are taking global unity transformation, not local unity transformation. So if you take the convex combination also, then if global unity transformation, when you are applying global unity transformation, and if entanglement will change, because global unity transformation may change the entanglement.
Yeah.
So
that's why.
Yes.
That's the question. So if you are already taking maximally entangled state, mixture of maximally entangled state, and global unitary transformation can change the, or convex combination can change the entanglement, then looking from the logical point of view, it doesn't seems to be that it will give you.
No, it will not maximally entangled mixed state then.
So that's my question is then what is actually. So that means.
So that means yes. That means
we can only.
Yes. In that sense. So that means it may if you apply global unity transformation again and again, and if you have certain point at that point, if the entanglement does not increase, then only you can say that it is a maximal entanglement mixed state. But if it increases, then you cannot say. So it is not the criteria, but there is some criteria given by Ishizaka and Hiroshima that when we have this type of thing, that when we don't have when we when we means what is the maximum number of times, or what would be the form of the state, what would be the form of the state, and that form of the state is given in terms of rank of the state, rank 2, rank 3, state of rank 2, state of rank 3. They have different condition for the maximal entangled mixed state to achieve the maximal entangled mixed state.
Yeah, so but that means the condition that it should be for a given
Depend on the
probability
parameter of the state.
condition. It's not the strict condition, right?
No.
Thanks.
What is MJWK states in this slide, that the last slide that you had open?
This one?
Yeah, MJWK states written there.
Yeah, that one.
So this was Muro statement that you asked question earlier also. That was a particular kind of MEMS.
This is a particular kind of MEMS state. So the form of that state is given by this one.
Yeah, but I checked this paper, and here you have already written this analytic form of MEMS. So which one is Monroe? All MEMS are Monroe states, or?
No. This is Monroe state actually. I have written here MEMS, but this is Monroe states.
Okay. And one quite unrelated question means, as you have mentioned, there are mixed entangled states which are not suitable for teleportation. Is there some kind of study for steering? Means there are states, mixed states, which show steering correlation, but are not suitable for teleportation?
Actually, I have no idea about steering because I have not worked on it. I have not even not read it, this steering. So, but I haven't seen any relationship between the steering and teleportation till now. Any other question?
Hello. When we look into the hello. So when we look into okay, sir. When we look into the density matrix form of maximally entangled pure state, but when we assume that we assume also the maximally entangled mixed state. So what is the basic changes or the significant change between the maximally entangled single state and maximally entangled mixed state?
Maximally entangled pure state has the highest entanglement, and that cannot be reached by maximally entangled mixed state. Now, the entanglement of maximally entangled mixed state is always less than the maximally entangled pure state, because it has some mixedness.
But what is the change between the density matrix form?
Density matrix form.
When I look into the density matrix form of the maximally entangled pure state and mixed state, actually, what is the significant change, significant difference between these? I mean that what is the mathematical changes between this state?
Mathematical difference, if you take two matrices and if you take the maximally entangled mixed state, then you can get either first element Then in the row, the fourth element means A11, A14, A41, and A44. These 4 elements are there if you construct the matrix representation of any maximally entangled mixed state. And then that means Bell state. Or you can have A22 element, A23 element, A32 element, or A33 element. Okay, so these are the 2 forms. Either if you express this as 00 plus 11 by root 2 or 00 minus 11 by root 2, if you express this as a matrix form, this state as a matrix form, then you can get A11, A14, A41, and A44. And if you have this A01 and 10 combination, then you can get A22, A23, A32, and A33, this form matrix element. So now if you have maximally entangled mixed state, so in case of maximally entangled mixed state, then some mixedness is there. There is trace rho square is less than 1. So that means you can get some other diagonal elements, other off diagonal elements also. So this is the change.
Okay.
Any other query, question? Kishore, should we discuss anything on control teleportation or keep it for a separate discussion?
Hi, there was a mention that it's easier to reclassify.
Not audible, Ashwin.
Ocean, तुम्हारा आवाज नहीं आ रहा है. Ocean, you can also write in the chat box.
I think अश्विन का ड्रॉप हो गया सर.
अच्छा, और किसी का कोई क्वेश्चन है? Anyone wants to add any comment or ask anything? So even if later some question come in your mind, means you can write directly to Satyabrata, means. So don't hesitate in asking questions.
Okay, can I ask question?
Sure, of course.
Yeah, so
Continue.
my question is regarding the classical fidelity paper that you were basically showing. So you were basically saying that prepare and the procedure is basically prepare and measure. So, and actually you were actually saying that by no cloning theorem, we can have the same copy which can be cloned. But in this technique, what they are actually assuming that they can have multiple copies of the same state prepared. So I think when the no cloning theorem basically prohibits that thing, then how can they basically assume that we can have basically n number of the copies of the same qubit? So this is my question.
Basically you want to ask that if no cloning theorem is valid, then how they can assume that they have n copies?
Yeah.
Actually, so they are taking it as in principle. In principle, if we can do this.
Yeah, but even in principle we cannot do this.
Actually,
then
okay.
How can they assume? So that's the thing I'm confused.
Just a minute. Let us suppose if we have so let us suppose alpha 0 plus beta 1 is given to you. Okay, and then if you don't have any if you have only one copy and you don't have any other copy with you, so what we will do, you will just apply the cloning machine operation to clone this state so that you can have more than one copy. Okay, so that means what you will do, you can just take 1 to n cloning machine. That means you have one original and you have to make n copies from there. So you can make n copies. So in this way you can have a cloning machine which which give you from one original, and you can get n copies from there. Okay, so since the cloning is not perfect, so what you will get in the at the output, that copy is imperfect. So that means what you want to copy the information, you cannot copy it exactly. So this n copy, maybe some information which is contained in this n copy is required by the other observer also. So that means you can have this n copies with you, and then you can prepare and measure strategy applying on that copy.
But
So it is
Satyabrata,
depend on you which type of task you want to do. So this is,
Satyabrata,
yes.
in this paper, do they talk about the cloning? Because I thought it's already given as an ensemble. So
Yes,
when
yes,
they
it is
are
ensemble. Yes, it is ensemble and ensemble copies. But he is asking that if we have only one copy, then how we can reconstruct the other copy in that similar state.
I thought this is not the even scenario in which context you are not talking in that context, because the paper says it should be given as an ensemble, and it is possible to, if you already have an ensemble of particles, suppose initially irrespective of whatever state they are, you can prepare you can apply a arbitrary operation, unitary operation, and prepare all the quantum systems in the same. So that is completely different than cloning the system. That is possible, that is permittable. But cloning is definitely, even in principle, not possible.
So if you apply the cloning machine, then your information is lost. Some information will be lost. Okay, so that's why you cannot apply this cloning operation there. So if you have one copy, that means you have taken one copy from some ensemble. Okay, so in that paper, what I have shown earlier in this paper, they have talked about the ensemble. Okay, they have an ensemble, and if you have ensemble of what we are saying, that so in the ensemble, if we have n quantum state, then in that ensemble you can just use the prepare and measure strategy, and from this measurement strategy you can perform the optimal measurement strategy, and with that optimum measurement strategy you can have this fidelity n+1 by n+2, where n is the number of particles in the ensembles. So if n goes towards infinity, then this goes towards 1. This fidelity goes towards 1. So this is the thing. But if you want to apply the cloning machine in a single copy, then your information will be lost, because you can apply, because cloning machine is not perfect. So you cannot apply cloning machine. So don't take this concept here, because it is totally different from cloning. So we are just explaining this thing with n ensemble, and if you're in n ensemble, if you have one copy, then the fidelity is 2/3. This is the only thing.
Okay, so for classical teleportation, we basically need an ensemble of states, but for quantum teleportation, we just need a one quantum state.
Yes.
My other question that I want to ask regarding this is that how is basically teleportation different from the broadcast of correlations or broadcast of the state?
So broadcasting is something broadcasting means you are just preparing from one entangled state to the two entangled states. So there you can you have two the broadcasting of entanglement means you should have one entangled state there, and from that entanglement you can create more than one entangled pair with lesser amount of entanglement. This is the broadcasting. And the teleportation means you want to send some information from one place to another place.
No, but it's not it like broadcast will at least 2 receiver, and here one
Yes.
receiver is sufficient. And the moment you have 2 receiver, then because of the no cloning, you will not have the perfect copy with the 2 people.
Okay, thanks.
Any other question? So Satyabrata, actually the control teleportation remain. So maybe means we make a smaller meeting means in for control teleportation sometime. Actually that is where Kishore and I stuck. Means we had some idea, and means of course in a different sense, means we were following Sohini Ghosha's paper, and we had some idea about somehow about programs. We still feel that our logically we are doing the right things, but the sense in which you are using control teleportation is different. But we wanted a discussion on control teleportation. So so this we are considering as a discussion 1 of a series of 2. So next time we'll start from the control teleportation, and it will be a mixed talk, more discussion. We will also tell that means what is our thought and where we stuck, and then we'll listen also. So so invitation for the next talk, and thanks for today's talk and all the discussion. And anybody means Arindam is the youngest PhD student in the group, and it's nice that he asked questions. And so if something more comes in your mind, you can ask later also. And thanks everybody for coming, and special thanks to Professor R.K. Sinha for joining us. And thanks Satyabrata for a nice talk, and we stop here.
Thank you, Anirbandha.
Bye.
Bye.
Thank you.